Hello, AP Stats. Hope you guys are having a great day. Today we're going to do the last section of 12.1, which is a significance test for slope of a least squares regression line. So our SWABAT for today is performing a significance test about the slope of a population regression line. Surprise, surprise. Okay, so main question is why would we even want to do a significance test for slope? Reason really is that there's either two possible scenarios. One is there's really actually no actual association between the two variables, therefore a zero slope, and the observed slope that we have is just due to sampling variability. Or there truly is an association between the two variables, so a non-zero slope. And so that's kind of what we're testing, and that's kind of what our hypotheses are going to be about. So remember, your hypotheses are all about the parameters. It's all about the population. Because we know about the sample, we know about the statistic, we want to infer information about the population. So our null hypothesis is going to be that the slope, the true slope of the population, or beta, is whatever the hypothesized value is. Usually it's zero just because we're assuming there's no association and the least squares regression line looks like this. But sometimes it might be something other than that. I just don't want to eliminate other possibilities. Which then means that the alternative hypothesis is that beta is greater than the hypothesized value, less than the hypothesized value, or not equal to the hypothesized value. Same thing we've always been doing, except now it's for a different parameter in a slightly different situation. All right, conditions. When you're making inference about a linear relationship, you have to do the liner conditions, L-I-N-E and R, linear. Okay, so L is you see an approximate linear relationship between the two variables. I, trials are independent, or if you're sampling without replacement, then it's the 10% rule, n is less than or equal to 10% of your population. For the linear condition, you have to look at both the scatter plot and the residual to get full credit. So scatter plot, you're just looking for a general linear trend. And then for the residual, you're looking for no pattern in the residual, because that means then that the line of best fit is probably a line, not something different like a quadratic or an exponential or a logarithmic function. So you're just looking, is the residual generally scattered and looks kind of like, wee, kind of like that, yeah. Can you see that? Yeah, all right. N is normal. You're looking for a normal-ish distribution of the residuals. So you can draw a scatter plot or a normal probability plot of the residuals for this check. E is equal variance. Equal variance is like looking at how spread out the points are from the least squares regression line. So something without equal variance would look something like this. Here's the least squares regression line, and there's like a bunch of values clumped together. They have a very small variance, and then like later maybe it like spreads out a lot more, and so the variance of the points changes. So something that would be good would be more like this, right? It's kind of like equally varied along the regression line. And last but not least is R, linear, right? R needs to be, the sample needs to be random. Or if it's an experiment, subjects are randomly assigned to treatments. The test statistic is T because you are estimating sigma, right? Sigma you're estimating with the standard deviation, or you're using your standard error, in which case you need to give yourself a little wiggle room. So you're using the T distribution, and the T test statistic is just like every other test statistic. Statistics minus parameter over standard deviation of statistic. In this case, our statistic is the observed slope of the least squares regression line. So that's B. Our parameter is beta, which is either your claim or your hypothesis value, which is going to end up being the same thing, right? So whatever your hypothesis was, your null hypothesis, that's going to be what your beta is. And you're dividing by the standard deviation of the statistic, which is the standard error of B. You're using the t-distribution with degrees of freedom n-2 for the same reason as before in the last video, but if you weren't paying attention then, it's n-2 because there are two variables that you are estimating. B, beta, is one that you're estimating, and then alpha, which is the y-intercept. You're estimating both of those, so you need to give yourself extra wiggle room for the t-distribution to find your proportions. P-value is the same thing it's always been, which is the probability of getting the statistic that you got, or anything more extreme than that. So, you know, on the distribution of t with degrees of freedom n-2. All right, so we're going to do an example. So we've got two stat students. They're investigating the effect of sugar on the life of cut flowers. So they went to a grocery store and they randomly selected 12 carnations. All of them seemed healthy when they started. When the students got home, they got 12 identical vases with exactly the same amount of water in each vase, and they put no sugar in 3, 1 tablespoon of sugar in 3, and then 2 tablespoons of sugar in 3 of the vases, and then 3 tablespoons of sugar in the last 3. And then they randomly assigned a flower to each of the vases, and then they checked how long it stayed fresh. So below is the data, sugar versus freshness, and then I also included your computer output and your least squares regression line and your scatter plot and your residual plot, and then also the histogram of the residuals. So you can check your conditions reasonably easy. So question 1 was perform a significance test to decide if you think that there's a linear relationship between sugar and the freshness of the flowers. Okay, we want to state what you're going to do, what significance level, and we also need to state our hypotheses. So I just said, well, we're performing a significance test at a significance level of alpha equals 0.05. See if there's a relationship between sugar of freshness and flowers. And then I need to state my hypotheses. So here are my hypotheses. I'm going to say beta is equal to 0. There is no relationship. That's my null hypothesis. Alternative hypothesis is that it is not equal to 0. So this is a double-sided test. And I basically picked a double-sided because in the problem it says the students decided to investigate the effect of sugar on the life of cut flowers. So it doesn't specify whether or not they're trying to test if sugar increases the life of cut flowers or decreases it. So they just want to know, is there an effect? So I set it as a double-sided test. All right, check conditions. Since it's a linear regression test, we need to check the linear conditions. L, do we see a linear relationship between these two variables? And again, like I said, you need to look at the scatter plot and the residual plot to get full points. So the scatter plot, yes, there seems to be a positive linear trend between the two, and since in the residual there doesn't really seem to be an obvious pattern, then we can say a line is probably the best fit. Okay, so say something like this-ish. Next condition is I, which is independence. So for independence, say something like, since all the flowers are all in different vases, you probably won't know the freshness of one based on the freshness of another. So it is likely that, those trials are independent. Next, you want to check normality of the residuals. So you want to look at the histogram of the residuals or a normal probability plot of the residuals. In this case, they give you the histogram, so that's what you want to look at and what you want to talk about. So if you look at the general shape of this histogram, right, you kind of see this symmetric-ish shape, and there aren't really outliers or skewness, and therefore you can check off the normality condition. Next is E, or equal variance, and for this one you want to look at the residual, and you want to look for, a general, the sameness of variability for all the X values. And this one, like you'll see, like here for this X value, the data points are a little closer together than, for example, here. But the thing is, we don't really see a pattern, like, very small variability and then increasing in variability as it goes along. So that's generally okay. So you might want to say something like the following. Although the variability of the residuals is not exactly constant at each value of X, there isn't a systematic pattern such as increasing variation as X increases. So you should be good to go there. And last but not least, random. The flowers were randomly assigned to vases, so we're good there. Now we need to calculate our test statistic, our degrees of freedom, and our p-value. So our test statistic is our statistic minus parameter, or standard deviation of statistic. Our statistic is whatever our slope was. Parameter was what our claim was, and then our standard deviation of statistic was our standard error of B. And all of those values, I believe, are on the data set up here. So this sugar in tablespoons, this guy here is your observed slope, so 15.2 is B. Beta is our claim, and we claim that our null hypothesis is that there was no relationship, so that's 0. And our standard error we can get again from our computer output, and it says our standard error coefficient is in this column, but we want it for sugar, so that is our standard error, 1.943. Even more awesome is that they also give us our t-value and our p-value. So if you go up again and you look, the t for our sugar is 7.82, that's our t-value, and then our p-value, right, the probability of getting our slope, 15.2 or anything more extreme, is 0.00. On Minitab output, this is always for a two-sided test, and so if you're doing a one-sided test, you want to divide that by 2, but we did a two-sided test, so, and it doesn't really matter because it's 0. In this case, it would be 0. Okay, so let's fill those in. Our degrees of freedom is our sample size minus 2. And now that we have our p-value, which is 0, we can conclude, and we're going to, because our p-value is so small, the probability of getting our observed value, assuming the null hypothesis is true, is so small that we want to reject the null hypothesis. So we conclude something like the following: since our p-value is less than 0.05, our alpha level, we reject the null hypothesis. We do have statistical evidence to say that there's a linear relationship between sugar and freshness in the type of flour. And you can include in here positive or negative if you started out with a certain null hypothesis, like if you're only testing that beta is greater than 0, then you can conclude that there is a positive relationship. We did a double-sided, so I'm just saying a linear relationship. That's it. So I entered all my data into list 1 and list 2, and you can also do this test. If you go to linreg t-test, and you have all your data in L1 and L2, you pick a not equals to, because that's what we did, was a double-sided test, and calculate. We have all of this information, our p-value, our degrees of freedom, and even your line of best fit.